Yeah. So,
Perfect. All right.
yeah, Santanu
So
and new announcements to be made, I guess.
no
Um,
announcements. So just
yeah. So,
yesterday.
as before, just please either raise your hands, your virtual hands, or feel free to ask questions on the Zoom chat, and then I'll interact if needed.
All right. So last yesterday we stopped at this result by Tawarmalani, Risha, and Chung, which said that if you have this a covering bilevel set, which is unbounded, by the way, the only time I'll consider an unbounded set. Well, that case, the convex hull is given by this set, and we discussed that, in fact, this is a reasonable description in the sense that this is convex and set, and in fact, the square root times xy is a positively homogeneous function, and that somehow this is going to be important. All right, so let's quickly see the proof of this theorem. The proof that I'm presenting here is in some sense innocuous, and I guess a bit different from the original proof. The original proof is far more important in some ways, and I'll talk about why it's far more important, because the theorem actually is not about this particular set. It's a much more general result in this paper, and I'll try and make the connections. All right, so okay. All right, so as usual, one side of the proof is usually easy. So this side is easy. So I want to prove that this set with these square roots, sum over square roots xi, yi, this set here is containing the convex hull of this bilinear covering set. And you see that this is not so difficult, because what I have to do is I have to take any point in my set P, right, and show that it's in this set. So of course this is convex set, then conv of P would be contained in this. So if you take any point in set P, which is satisfying this bilinear covering, well, there are two cases to consider. Either you have some index I such that xi, yi is already greater than or equals to 1. Well, in that case, the square root will be greater than or equals to 1. And since everything is non-negative here, this sum will be greater than or equals to 1. Or for each index I, this product here, xi, yi, would actually be less than or equals to 1. But then we know that, in fact, the square root for each term is going to be greater than each of these term by term, and this was in P, so this is greater than 1, and so it satisfies. Okay, so therefore, clearly anything that is in P is actually in this set, and so therefore conv P is contained in this set because it's a convex set. All right, so let's do the opposite side of the proof, which is sort of the more important side of the proof. But as I told you, it's just a hacky kind of a proof that I'm presenting because it's shorter. But I'll discuss sort of the more general result in this paper next. All right, so let's take something in the set H. H is this, what I call as this set with the sum of n terms, each of them with the square root xi, yi greater than or equals to 1. So now what I want to do is take something in H and basically show that that guy can be written as convex combination of points in P. All right, so how do we do that? So let's take this point here, and okay, so this is not completely general proof. I'm just assuming that there are 3 terms where xi times yi is non-zero. Okay, but there could be more points like this. And for all other terms here, xi times yi is 0. Maybe one of them is positive, right? Or both of them could be 0. That's totally okay. So that's how my point looks like. That is in this H set, which is the summation of n square root terms, each square root term being xi, yi greater than or equals to 1. All right, so now let me call this square root x1, y1 to be lambda 1, which, as I said, I assume is positive, lambda 2, and lambda 3. Now, all of these, one of the x's and y's is 0, so this product is 0. And so then I know that lambda 1 plus lambda 2 plus lambda 3 is at least 1, because I assume that this point is in H. So let me just normalize these lambda so that they look like multipliers in a convex combination. Oops. So this is this lambda I check, which is this lambda I over the sum of these lambdas. And then basically, again, it seems like a very straightforward proof. What you just do is you take these points. What I did is I take x1, y1, and then I take all of these 0 guys, and I scale them by lambda 1 check, right? I took the second guy, and the second guy and third guy were zeroed out in this first point. For the second point, I zero out all the blue guys and this, I guess, purple guy, and this green guy gets rescaled by check 2, and then for the third point, I pick this guy, I rescale x3, y3 by check 3, zero out everything. All right. So it's easy to see that if I multiply this guy by check 1, multiply this guy by lambda 2, check lambda 2, multiply this guy by check lambda 3, add them up, I get this point. This is easy to see. So clearly, this point here is a convex combination of these points. The question is, are these points in P? If they are, then I'm done. It turns out it is. If you do, again, it seems very algebraic here and does not seem to give much intuition. But if you just, for example, multiply these two terms here, I can rewrite this as the square of the square root of that divided by this check lambda 1. Well, this one is at least lambda 1, we know. And because I'd rescaled, check lambda 1 is less than lambda 1 because this was supposed to be greater than or equals to 1. And so everything works out. All right. So it's a very almost very algebraic, non-intuitive proof. But there's a reason why I've highlighted this. So, and let me get to the next slide for that. But basically, this completes the proof as is. All right. So I could take this point in H and I could rewrite them into these points. Obviously, I'll need more points if there are more terms that are positive, and everything works out. So actually, what this paper really shows is a little bit more general. It talks about.
Sorry, Santanu, can you go back one slide? So in the definition of the points, so what happens exactly to the last n-3 components?
Oh, they are. I am assuming they are 0. The products are 0. It could be
the products, but the individual points. Okay, I guess. Oh, okay. So you just put them all in the first one?
Yeah, the 0 guys I just put with the first one. I could have put it with the second one. That's
right. Yeah, I see. Yeah,
that's just the calculation. Yeah, exactly. Very good. Yeah, and so so what they really prove is actually a little bit more general. They actually talk about much more general polynomial covering systems, and basically what they say is, as it turns out, this particular example also has this sort of so-called orthogonal disjunction property. What does that mean? If you define the set Pi, which is in this 2n space, but you just say xi, yi is non-negative, right? And then everything else is a cylinder. Then it turns out that the extreme points of these Pi sets are orthogonal to each other. That's why the word orthogonal. But in fact, convex hull of P is precisely given as the convex hull of union of these guys, these Pi's. Okay, and you can explicitly check this. What is more interesting is that the description of Pi, I've written like this, but this set here, when I have just one term, I don't have multiple terms, so it's a covering set, but with just one term, this actually is a convex set. But in a sense, it's not the right way to write the convex set. If you really want to write the convex set with concave functions with a greater than equals to, this would be the right way to write the set. These two sets are exactly the same, but with the square root. But what is nice about this description is not only is this function here concave, but it's positively homogeneous. So what these guys actually prove is that whenever you have this sort of orthogonal disjunction property, and simultaneously the convex hull of each of these pieces can be written in some form like this, where you have this concave function greater than or equals to 1, but the concave function is also positively homogeneous. Then basically what you do is you take these concave functions and you just stick them together, and that gives you the convex hull. Okay, and to give you one more example, and I'm not presenting the general theorem result here just because there's a lot of technicalities and notation that you have to get into. But essentially, this is the story. If I have to explain it as a story, and just as an example, now here is it's not a bilinear system, but here's a product of 3 guys. But it turns out the convex hull of this guy basically looks like this. X1, X2, X3's amount does not interact with 4 and 5 and does not interact with 6. And so it turns out each of these convex hulls separately looks like X6 greater than or equals to 1, square root X4, X5 greater than or equals to 1. And this is the cube root of X1, X2, X3. Where if they're non-negative, this is again concave function, positively homogeneous. That's the convex hull of that set. And because of this orthogonal disjunction, you could just stick them in. Okay. I'll just say that. I think that conveys the message of the paper, but you should really look at the paper to see all the sort of the nuances and technical details that go in to prove this. But this positive homogeneity really plays an important role. And in fact, this I had put this in the box because this calculation, there's like a more general version of the calculation, goes through because of positive homogeneity of the square root function. That's what's going on. All right. So let's move on. So this up until now, so what did we do? So yesterday we looked at we first talked a little bit about convexifying functions by the convex envelopes. Then we start talking about sets. We talked about the simple bilinear system where we talked about the McCormick envelope giving the convex hull. We looked at the generalization of that, which was this sort of simultaneously convexifying products where you don't have xi squares. So you have x1, x2, x1, x3, and so forth. And the convex hull was this Boolean quadric polytope. Then we looked at the packing bilinear set. And then we looked at this interesting set which was the product of variables, one living in a simplex. All of those cases, the convex hull was a polytope, even though the set was nonlinear. But this was the first example where the convex hull is not a polytope. It's this with this square root function. But what I want to talk a little bit about is that this set here, it's not LP representable, obviously, but it's in fact a second order cone representable. And I'm just going to quickly go over this. I don't want to spend too much time, but I'm just going over to make sure that everyone knows what this is, assuming someone has not seen it before. But I assume most of you have. So what is this business of second order? Oh, okay. Never mind. Let me just, can I just give me a second. This is, sorry, my apologies. Okay, maybe this is a better version of the talk. Okay, sorry. This is the better version. Sorry, just let me just quickly go through this. That's a review. What do we have seen? Oh my God. Okay, good. Screen. Hello, can you still see my screen? Hello?
No, we cannot.
Oh, really? Okay. Okay. Oh, okay. What should I do? Share screen?
You're not sharing. You're not
Okay.
sharing your screen, Santanu.
Is this okay now? Can you see my?
Yeah.
Yes. Yes.
Full screen mode. Can you still see it?
Oh,
Yeah.
it's the same. It's the
It's
same
the
issue
same.
as before, Shantanu. Maybe you want to share your entire desktop?
I want to set that exactly. I want to do that. Yeah. Desktop share. Now can you see it?
Yep.
Oh, okay. Yeah. Sorry, my bad. Okay. So, all right. So let's talk about the second order cone representable set. So what is that? So a polyhedron in general could be written as ax minus b greater than or equals to 0. So that's just saying, look at all x, you apply this affine map, and then the image should live in this cone, non-negative cone. What is the non-negative cone? That's just a closed, convex, pointed, full dimensional cone. And so what you can do, one natural way to generalize a polyhedron is to talk about a generalization where you replace that cone with any other cone which is closed, convex, pointed, and full dimensional. Pointed means that there are no lines in the set. And so that would be a conic set here. So for example, now again, give me the set, look at the set of x's so that this affine image of this set ax minus b lives in this cone, which is not polyhedral. So these are conic sets. All right. And so now this is a conic set, just the set of x such that ax minus b is in the cone. And for polyhedron, this cone is Rm plus, but for the second order cone, it's a cone in Rm, but it's a different cone. It's a cone where you say that the 2 norm of the first m minus 1 components is less than the last component's value. Okay, and we say a set is second order cone representable if you're living in X space, that exists some y, and you take the projection, there exists some y, such that when you take the and there exists some sort of this affine mapping, so that when you apply this to x and y, what you do is you get a vector which lives in the product of these second order cones. If you haven't seen this before, the second order cone generalizes polyhedron. So any polyhedron can be made to look in this form, and you'll see in a second why. And SDPs are a much more general class. So anything that is SDP representable, so any set that can be described using a semi-definite programming feasible region is a generalization of a second order representable set. And one more way to see this in a more algebraic way, if you have not seen it, is just to say, okay, so it's the set of x such that there exists y, so that there are these p different affine images, such that the first m minus 1 components of that image 2 norm is less than the last component, and there are p of them. So there are p of such constraints, and the projection to the X space is the set S, and this is second order cone. All right, so why I'm going through all this, as I said, that the second order cone is a much more general, richer class than LPs. You can optimize on second order cone representable sets. And while the solvers are not as good as LP solvers like GuroB, Cplex, Skip, and etc., there are some very good solvers for second order cone representable sets. So Mosaic in particular is a solver that at least I use quite a bit, which scales really well. Mosaic does a decent job with SDPs as well, but second order cones you can really scale very well. So it's not as good as an LP solver, but it's quite good. So if you have a set that you can describe using second order cone, you expect to solve it well. And why are we going through all this? Because we want to really say that this set here, which was our convex solve, was not polyhedral, but it turns out it's second order cone representative. And how do we see that? Well, this set is nothing but x and y is non-negative. And what I'm going to do is I'm going to replace this term here, each term here, by essentially a new variable, let's call it ui. So then this becomes summation of I going from 1 to n, ui greater than or equals to 1. And now I connect the square root term. So I say square root xy is greater than or equals to ui. Well, but then this is the same as saying xi yi is greater than ui square. But that's the same as saying xi plus yi square minus xi minus yi square. The square terms will cancel out. I'll be left with 4 xi yi. So I multiply 4 here for ui square. And this is all, by the way, very standard. If you've not seen it before, it's new to you. Otherwise, this is super standard. And now this, I take one of these guys, I put it on the other side, and take square roots again. And now this here is nothing but the 2 norm of this term 2 ui and xi minus yi. And these things look like polyhedral, but as I said, anything polyhedral can be made to look at second order cone representable. And that's just because I can write that as xi is greater than 2 norm of 0, yi is greater than 2 norm of 0, ui minus 1 is greater than 2 norm of 0. That's the same, that's non-negative. And this term is greater than 2 norm.
Sorry, Santanu, just a question on the chat. Asking whether the second order cone solvers, are they only for continuous problems, or do they also support integrality conditions?
So there is mixed integer SOCI solver. So Mosaic supports that, Gurobi supports that, Skip supports that, yes. So they do have also SOC IP solver, most of this. There are more generalizations of this SOC cones called as power cones, and there are other cones like exponential cones, and I believe Mosaic supports those also with IP. All right, so, but is this a go? Is this clear? So essentially, this convex hull that we got for the bilinear covering set is second order cone representative. Very good. All right, so that's pretty much where. So now, basically, what I'm going to do now is present essentially one last result on convex hulls of sets. But this is going to be a much longer presentation. And this is essentially this result that we obtained last year with a student of mine, Asteroid Santana. Yeah, this is not a typo Santanu Day. This is actually Santana. And essentially what we proved is, well, it's not a generalization of the previous result, because as I said, the previous result was for an unbounded set. But basically what we were able to show is that if you take a set which is described as the intersection of a polytope, and one quadratic equation, it's an arbitrary quadratic equation, that the convex hull of this set is second order cone representative. Okay, so this is just an arbitrary Q, symmetric Q matrix, and this is any arbitrary polytope. So this generalizes definitely the sort of the packing set and some of the other sets that we discussed before in some sense. The proof is constructive, and so in a sense it builds the convex hull. We don't get any nice sort of complexity type of results because in a sense, optimizing a linear function over this set is, or checking whether this set is, I think, empty is NP hard. And so in a sense, the description, we assume that the set S is non-empty, that the description of this SOC representability is exponential. So it has to be exponential in that sense. But also what is nice is that this result would also hold if, in fact, in a sense, with an easier proof with the inequality. You could also take inequality and reduce it to equality and see that the result holds. If it's an equality, you just add a new slack variable. Because everything is bounded, if everything else is in a polytope, the slack would also be bounded. And so you'd get into an equivalent system, which is equality, where everything is bounded and the result would follow. All right, so in order to prove this result, actually, I think the proof of this result uses one, I think, an interesting tool, but which we had to come up with. But there are other lots of very surprising results actually that we had to use. That I find still today very surprising after looking at them for the last year or so, which I really wanted to cover in more detail. So these are sort of the building blocks that we use. The third one is sort of, I think, kind of also. Most people who do integer programming would understand this and know this. But these two theorems, I think, are quite interesting theorems that are building blocks towards proving this theorem. So let's sort of spend some time in going through these results in detail. So the first one is going to be the Hillestad-Jacobson theorem on reverse convex sets. The other one actually is unpublished by J.P. Richard and Mohit Tawarmalani. I keep asking them to publish it. It's an unpublished manuscript. I call it the Richard Tawarmalani lemma because, yeah, it's a very interesting result. Okay, so let's go through these things. So reverse convex sets. Okay, so what is reverse convex sets? So reverse convex sets is essentially a set of the following form. It's some polytope. Well, in general, reverse convex sets could be a convex set here, but for our purposes, it's a polytope where you remove, and these CIs are closed convex sets. And what you're doing is you're removing the interior of these closed convex sets, a bunch of them, all right? And there's a rich history of studying this set in the global optimization community. This is related to something, I didn't make the reference here in my slides, but this is related to something called as TUI cuts. But this is something that people have looked at a lot in integer programming as well. And that is in the context of intersection cuts. So what happens in integer programming? We have our favorite polytope. We are interested in optimizing with the integers on this. we solve the LP relaxation, we get a fractional vortex. We want to get rid of the fractional vortex. So how do we get rid of the fractional vortex? Well, we come up with a lattice-free convex set. So a convex set which does not contain any integer point in its interior. So in a sense, we know that everything that is in the intersection of P and C, there is no integer points here. And so what I want to do is now get a linear cut actually. And the name intersection comes because you just sort of look at where this cuts off and you draw a line through that. And that's why it's called the intersection cuts. This was introduced by Egon Balázs. And you get these cuts for integer programming. As it turns out, in this case, as you see, this M was 1. I just remove P minus the interior of one convex set. It turns out the convex hull here, you see, is a polytope. Let's do an experiment where I remove more sets. So here's a polytope, and now I'm removing 3 convex sets. And so my feasible region is sort of this line segment, then this, and this, and this, and this piece, and as you look at it for a little bit, you'll see that the convex hull here is again a polytope. And so that is the sort of the magical result, which is a bit surprising when you see it for the first time, is that if you take a polytope and you take a bunch of these closed convex sets and you remove the interior of these closed convex sets from P and you take the convex hull of that, it's again a polytope. Okay, and so we'll prove this in completeness. The proof is actually quite nice. I think it's from this 1980 paper. I've adapted the language to make it a little bit more modern. And again, the proof is based on this sort of Krein-Milman theorem. Basically, what we'll show is that this set S, which is a polytope minus the interior of a finite number of closed convex sets, has a finite number of extreme points. And so, of course, when you take convex hull of it, it is a polytope. All right, so what we'll do is first is we'll jump into a necessary condition for a point being extreme point of this set S. So remember, again, S is a polytope where you take away the interior of a bunch of finite number of closed convex sets interior, you take that away from P, and that is S. So the necessary condition is the following. So let F be a face of this polytope of dimension D. And if you take any point in the relative interior of this face, so F is a face of P of dimension D, if you take any point in the relative interior of F, then for X0 to be an extreme point of S, it must belong to the boundary of at least D of these guys. Okay, so remember the M of these guys. So now I take a point X0, which is in the relative interior of a face F of P. The dimension of F is D. X0 is an extreme point of S. If, no, it's not an extreme point. If it is an extreme point, I should have written it that way. If it's an extreme point, then it must be on the boundary of D of these guys. All right, so let's see why this is true. So let's take this point here, which is in this two-dimensional face of my polytope, and it's, you see that it's not an extreme point, right? I can kind of wriggle it a little bit, and I'll still remain in my feasible region, and that's what I want to prove. That because this guy is in a relative interior of a two-dimensional face, but it's in the boundary of only one of these guys, it's not an extreme point. All right. So a little bit more formally, so X0 is in the relative interior of F. It's in the boundary of K guys, where K is less than D. K here in this picture is 1, D in this picture is 2. All right, so it's actually the proof is via separation theorem. So I know that this point does not belong to the interior of C1. Interior of C1 is also a convex set. So I can actually find an inequality that separates this point from the interior of C1. Now, of course, this inequality will pass through this point. So basically, I'll get K of these inequalities. In this picture, I get 1 because this K is 1. And I put these equations together, I call this set V. So in this particular example, V is just this one-dimensional line. In general, it would be, because this is also a two-dimensional picture, in general, so there's k of these equations will be a n minus k dimensional affine subspace that contains my point x naught. All right. And you can check that this dimension will be at least one by one way to see that, for example, is that dimension of this set here, the affine hull of this face intersected with V is at least one. And one way to check that is F was d-dimensional. So one way to think about affine hull of D was that you obtain that by n minus d equations. V was obtained by k equations. So this object here has n minus d plus k equations, but k is less than d, so that there must be at least some wiggle room. Okay, so that's one way to see it. All right, so we've done this part. Next, what I can do is I can put a ball around my point x naught. This is, you think of this as a full dimensional ball around x naught with the following property. So remember, x naught was on the boundary of C1, or the first k guys, right? But x naught was away from the other guys. So this ball is constructed in such a way that this ball does not intersect with these other convex sets from k plus 1 to m. So in this picture, this ball does not intersect with C2 and C3. Okay. All right. So then we can now do a little bit more calculations. This object here, affine hull of F, intersected with V, which was, remember, all these separated inequalities when I set them to equality. We've already calculated its dimension to be at least one. This is just full dimensional ball. So this dimension is at least one. And also, just because of the way I've constructed it, you can check that this ball intersected with this line is not contained in the interior of any of these balls, but it's in fact contained in F. In other words, I can basically take 2 points on this line, that is 2 points on V, basically 2 points in this set here, and I can take 2 points that are different from x naught because the dimension was greater than 1, and so therefore this point cannot have an extreme. Okay, so this is just going through the details. You probably have to write a little bit more to make it a completely formal proof, but you see why this is true. So again, if you have this polytope and you're removing m convex sets, interior of convex sets, and this resulting sets, if you are interested in its extreme points, if you take a point in the relative interior of a face of the polytope, with the face has dimension d, then you better be on the boundary of at least d of these convex sets for it to be an extreme point. All right, good. As it turns out, this already proves the result of the theorem for the case when you're removing one convex set. Why? Well, if you're removing one convex set, notice if you take any point in the relative interior of a face of the polytope, where the face is dimension 2 or higher, for it to be an extreme point, you would have to be on the boundary of at least 2 convex sets or more, but you are removing only one convex set, right? So that means that all the extreme points of the set S must be points of the form where you take one-dimensional faces of a polytope, that is edges of the polytope, and you're on the boundary of this one convex set, all right? But then if you take lines, you see, you take away convex sets, or if you take a line, literally a one-dimensional line, and you take a convex set, you can get only 2 intersection points at most, right? And so therefore the number of extreme points, the extreme points that you get are just either the extreme points that were not cut off by the convex set originally, extreme points of P, or they're points on the boundary, these edges of P intersected with the boundary of this one C1, which can also be only finite, and so the number of extreme points is 1. And this is the version basically we kind of use in integer programming. So this first lemma is enough to already prove when you're removing one convex set. It's not enough to prove the theorem in general, mostly because you see that this result is not a sufficient condition. So here I have this polytope P. First of all, you can see that what can happen is that in higher dimensions, when I say higher dimensions, when you're taking a face of the polytope, and the face is dimension 2 or higher, you can have these convex sets where there are portions of the boundary that completely match up. And so there can be an infinite number of points that satisfy the condition of the previous lemma. And so they will not be able to distinguish. But more importantly, this simple example shows that the previous lemma is not if and only if, right? So if you take this polytope here, and I'm removing C1 and C2, and okay, this C1 was supposed to be convex, but I was a little drunk, so this is a drunk convex set. If I remove this set, this S is my feasible region. Now the previous lemma would say, look, this point here this is a two-dimensional relative interior, two-dimensional face. This point here is a boundary of two guys. So this could be an extreme point. So this cannot be an extreme point, this cannot be extreme point, but this can be extreme point, this can be extreme point, this can be an extreme point, and so forth. So these guys can be extreme points, but turns out for the convex hull of S, none of these guys are extreme points because this is the convex hull. Okay, and so lemma 1 is enough to prove in the case when m equals to 1, but you need a little bit more to prove it in, when you're removing more convex sets. And it turns out the key idea is this idea that I call as dominating pattern idea. And the idea is the following. You take 2 points in your set S. We say that x2, the pattern of x2 dominates the pattern of x1. Okay, if the following happens, x1 and x2 belong to the relative interior of the same face of P. So we're talking about one face of P, and we're taking points in the relative interior of this face. And then we say x2 dominates x1 if this second condition holds. Basically, if x1 is in the boundary of a certain convex set, then x2 is also on the boundary of the second convex set. x2 might be on the boundary of more convex sets than x1. But so if x1 is the boundary of C1, C7, and C10, then x2 is on the boundary of C1, C7, and C10. And what is the lemma? The lemma is that you take x1 and x2 to be distinct points. And if the pattern of x2 dominates the pattern of x1. So again, remember, that means that x1 and x2 are living in the relative interior of the same face of P. And whenever x1 is on the boundary of a certain convex set, x2 is also on the boundary of that convex set. Then x1 cannot be an extreme point. Okay, and maybe if we just look back here, you see, these guys each dominate each other. For example, this guy is on the boundary of this convex set and this convex set. This guy is also on the boundary of exactly the same two convex sets. So that lemma says this cannot be an extreme point and this cannot be an extreme point, because this guy dominates this guy and this guy dominates this guy. Okay, and why does this prove the theorem? Basically, so as we said, we want to prove that the total number of extreme points of S is finite. So now you explore, by lemma 1, I know that if I take a point, I take a potential extreme point, which is in the relative interior of a face of the polytope of dimension D, then I better be on the boundary of at least D of these convex sets, right? But then basically, now you do the following. Fix the face and fix your favorite, which is D-dimensional, and fix your favorite D convex sets that you want to be on the boundary of. There can be at most one such extreme point, right? Because if there were two such points, one of them would dominate the other, and so it wouldn't be the extreme point. And so therefore, since the number of faces is fixed, and since the number of convex sets is fixed, it proves that the number of extreme points is finite. Is this argument clear? I just repeat it one more time. Basically, I'm searching for extreme points. I take a point in the relative interior of a face of D dimensions, then I know that I'd better be on the boundary of D of these convex sets to be extreme. All right. But then the claim is that for any choice of D convex sets, there can be at most one extreme point like that. Why? Because if there were 2 points in the same relative interior of the same face that were on the boundary of the same D convex sets, then one of them would dominate the other, and so there can be only one such point that is extreme, and so then. All right, good. So
sorry, Santanu, can I ask you? So again, what the pattern is, all the of an extreme point of a point are all the convex sets that it's on the point is on the boundary of?
Yes, exactly.
But then I don't understand, if you fix D convex sets, one could be on the boundary of another convex set, and the other one could be on the boundary of another convex set.
That is allowed, but basically for any fixed set of D, if there are multiple points that are tight, then they will dominate each other. So here's what I would do. Okay, so maybe a different way to argue this is look at all subsets of your convex sets.
Yeah.
So take a particular subset, say, let's take the subset 1, 5, and 10.
Mm-hmm.
Then all the points that are tight exactly on 1, 5, and 10,
mm-hmm.
there can be at most one of them that is extreme point. Okay. In fact, none of them will be an extreme point, only when, because they will each sort of cancel out each other. But if there's a point that is on the boundary of 1, 3, and 10, and 11,
mm-hmm.
that would dominate each of these 3 points. Right? And so therefore you get finiteness.
Right. Okay.
So in some sense, basically what I'm saying is look at all subsets at which you have points that are tight,
mm-hmm.
then look at all the maximal subsets like that.
Mm-hmm. Yeah.
Right? And those would contribute to extreme points.
Right.
And each maximal would contribute at most 1. And so therefore there's finite.
Yeah.
All right, so basically what remains to prove this theorem is to complete this proof of this lemma, this pattern business. So let's check this. So here's the setup. So I assume x2 dominates x1. So x2 and x1 here live on the same face of the polytope. Okay. And whenever x1 is the boundary of a convex set, x2 is also a boundary of the same convex set. So x1 is the boundary of C1 and C2. So x1 is the boundary of these 2 convex sets. And you see that x2 is also on the boundary of these 2 convex sets. Okay. And there's a bunch of other convex sets, say x3, C3 and C4, for which x1 is not on the boundary. And I don't care about x2. All I know is that whenever x1 is on the boundary of a convex set, which is C1 and C2, x2 is also on the boundary. And now what I want to prove is that x1 cannot be an extreme point of my set S, which is somehow something like that, right? Okay. So here's what we do. Again, like last time, we construct a ball here, right? Full dimensional wall. When you intersect it with the affine hull of this face, you get this yellow guy. And this yellow guy is constructed in such a way that it does not intersect these far off convex sets. So C3 and C4, right? So this ball intersected with this affine hull of F is contained in F, and it does not, this X1 was tight on the first K convex sets. So was X2, because X2 dominates X1. And from K plus 1 to M does not intersect this ball, right? So this is what we'll do. We'll take this line segment between X2 and X1, and because they both live in the relative interior of the same face, I can extend this line segment and I'll still remain in the relative interior of this face, and I'll also remain in this ball. So I'll take some point x0, which is in this ball, so that x1 is the convex combination of x0 and x2. And basically, I know that x1 and x2 are feasible points in S. If I show that x0 is also a feasible point, or is in S, well, then x1 cannot be an extreme point. Okay. So how do I show this? First of all, note that this point here is in this ball, and so and this ball is contained in this face, so it's definitely in the face, and so it's definitely in the polytope. All right. Second of all, these far off convex sets, because they don't intersect the ball, this point is certainly not in these balls. So I don't have to worry about these far off convex sets. All right. Finally, you take this x0. Suppose this x0 was actually in the interior of this closed convex set, so C1 and C2. If it was in the interior of C1 and C2, because of the way these points are constructed, because x2 is on the boundary of C1 and C2, and x0 is in the interior of C1 and C2, then any point in the convex combination of x0 and x0 would actually be in the interior of C1 and C2, right? So, I mean, of course, you cannot construct a counterexample because that doesn't happen, but this one is on the boundary of C1 and C2. If this point was actually going to be in the interior of C1 and C2, so there was some small ball around this point here that was in the interior of C1 and C2, this guy is a convex combination of these two guys, that this guy would be in the interior of C1 and C2. But that's a contradiction because this guy I know is on the boundary of C1 and C2. And so this point here could not have been in the interior of C1 and C2. Therefore, at best, it would have been on the boundary of C1 and C2, but that's feasible. You're only removing the interiors of C1 and C2, and so therefore x0 is in S, and therefore x1 is not an X. Okay, any questions? All right, very cool. Then let's okay, today I'm actually speaking faster. No, we'll see. All right. So this is actually, it's a very surprising result. If you take out one convex set, it's sort of believable. If you take multiple, to me it was a very surprising result. By the way, we'll actually, to prove the theorem that I stated, we only need the case m equals to 1. But I did want to present this more general result, which is, I thought it's one of the super nice results that I've seen recently. All right, so now next, I want to deal with these equality sets. Remember, I had this quadratic equation, and equality sets are always much more difficult to deal with. But there's this beautiful lemma that JP Richa and Mohit have that was very useful in this analysis. And so this is, again, a sort of surprising result. So this is the result. So take a set of this following form, okay? P is any convex set, and the set is described by intersection of points in this convex set and this constraint fx equals to 0, where the only condition I ask for is that f is a continuous function. Okay, it doesn't have to be convex or anything. So it's just a continuous function, fx equals to 0. And x is in some convex set. Then it turns out that the convex hull of S is actually equal to the convex hull of S less than intersected convex S greater than, where S less than is fx less than equals to 0, greater than is fx greater than equals to 0. And you know, the set S obviously is the intersection of this set and this set. And of course you have this, you always have this inequality, right? So convex hull of A intersection B is always contained in convex hull of A intersection convex hull of B. But there's equality here because f is continuous. Okay, and so let's see the proof of this result. It is very surprising in my point of view. It's not easy to see why this is true. The proof is, at least I think these guys had multiple proofs for it, but the proof that I'm presenting is a proof that JP Richard shared with me, which is a very sort of algebraic proof. All right, so as I said, clearly S, which is described by fx equals to 0, and this by fx less than equals to 0, and this fx greater than equals to 0. So clearly this holds just by usual fact that convex hull of A intersection B is contained in convex hull of A intersection convex hull of B. So really what we have to prove is the opposite direction. And so we do it the usual way. We pick stuff here. We pick stuff in the convex hull of S less than intersected convex hull of S greater than, and we'll have to show that it's actually in convex hull of S. All right. So let's take okay. So this point is in both these sets, but let's just take one of them. So x0 is in the convex hull of S less than. The first claim is if this holds, then I can write x0 as a convex combination of points actually in S, so in the equality sets, and at most one set from the inequality set. Okay. All right. So let's see what's going on. So I have this set x0, which I write as convex combination of these yi's, where these yi's, oh, this is a typo here. This should have been less than equals to. This should have been less than equals to. So, I mean, I've drawn a picture here. I don't know if you like pictures of this kind or not. You can think of this blue line as fx equals to 0. Okay, and everything yellow here is fx less than equals to 0. And so all these 4 points are actually in less than equals to 0. And so x0 is in convex hull of S. And as you see here, none of these points, at least right now, actually satisfy this condition. They are not in S, right? So let me pick 2 guys, y1 and y2, which are in less than but not in S. Okay, and what we are going to do recursively is going to basically, we are going to rewrite this convex combination using some other points, where the number of points that I use from S less than equals to reduces by 1. So if I am able to do that, then I'll be done. Okay, so there are 2 cases to look at. So I look at y1 and y2, and I look at the correct convex combination. So you take these weights and you take the weighted average. So basically you have this y0. So we know that x0 is a convex combination of y0, x3, and y4. As it turns out, in this first case, we were lucky. This convex combination is also in S less than equals to. Okay, and so in fact, I just replace y1, throw away y1, y2, replace it with y0, and now my point x0 is a convex combination of y0, y3, y4, which is 1 less point from S less. Okay, so this is sort of the easy case. So what's the difficult case? Well, the difficult case is when I take the correct point, which is a convex combination of these 2 guys, but it actually falls in S greater than equals to. So that I don't want to use. I want to use points only from S or S less than equals to. But now we use the intermediate value theorem. So I have this point here where fx is greater than 0. I have this y1 where fx was less than 0. So because the function is continuous, I know there is some point in between them where fx is exactly equals to 0. Similarly, between y0 and y2, I know that there is some point here, this point here, where fx is exactly equals to 0. Fx is exactly equals to 0. So what I do is basically I take y1 and y2 and I just start pushing these 2 points towards y0. Okay, by respecting the right convex combinations. And basically what happens is as I push them, one of them hits S first and the other one remains in S0, less than equals to 0. And so now I can basically replace the convex combination of x0 with y1, y2, y3, y1, y2, y3, y4 with this new y1, new y2, y3, y4, where new y1, as it happens in this case, is in S. The new y2 continues to remain in S less than equals to. And so I have reduced the number of points that I need from S less than equals to by 1 again in both cases. So I can just recursively apply this argument and arrive at the claim that if my point was in S less than equals to, then I can write it as a convex combination of points in S, except I might need at most 1 point. Basically what is happening is every time I work with 2 points, so I might be left alone with 1 singleton, which is in S less than equals to. All right, and so I need at most 1 point from S less than equals to S. All other things can be in S. So that's already good. We want to prove that this guy actually is in a convex combination of S, and we're sort of moving towards that argument. And the second step is the following. So remember, I want to take this point which is in this set, intersect with this set, and I want to show that it's in convex hull of S. Now, because x0 is in this set, we just saw that x0 can be written as convex combination of points like that, where each of these yi's are actually in S. Only one y0 is in S less than equals to. Applying the same argument on the other side, I can write this convex point as a convex combination of other points where wi's are in S, and there's just 1 point, w0, which is in S greater than equals to now. Okay? And now you know what to do. Basically, again, apply intermediate value theorem. I have this y0 and w0. I know there's some convex combination of these 2 guys that lives in S. There's a question? Yes, go ahead. What's the question?
Yeah, so the question is that don't we have a boundedness assumption for this lemma? So if we don't have, then when the extreme points of conv S less or equal be contained in S?
No, there is no boundedness assumption here. This picture is not necessarily. The blue line could have been unbounded. There is nothing. That's just how I drew it. I'm not using boundedness anywhere. I'm just using intermediate value theorem. Yeah, so this result actually is true even without boundedness. Yeah. Yeah, this claim is true here. I'm just saying, look at any 2 points. I take the convex combination, the appropriate convex combination, and that still lives in S less than equals to. Then in that case, I'm done. Or it does not live in, it lives in S greater than equals to, but then by intermediate value theorem, I can still find new points where I can reduce one guy from S less than equals to. So there's no boundedness here. And then I reach here. Sorry, did that answer the question? I guess whoever asked it.
Yeah, I think so. Thank you.
And then basically you see that this point was in less than equals to, this point is in greater than equals to. So I know again by intermediate value theorem, there's a convex combination of these 2 guys that lives in S, and that gives me the hint to actually just algebraically aggregate these 2 constraints in such a way that the combination of these 2 guys is precisely this point Z0, which lives in S, and everything else that I use will be from S, these Y's and these W's, and that will be equals to X naught. And so all of these points are in S. It's a convex combination, and we are done. Okay. In fact, a very nice question that I have is that, so this lemma works with 1 constraint, right? So if you could ask the following question, take two continuous functions, right? And now you could take the 4-way division. Less than equals to, less than equals to, less than equals to, greater than equals to. You can take 4 of these things. Is it true? Turns out it's not true. It really only works with 1 equation. What would be super nice though is it's clear that it should work a lot of the times when you have multiple constraints. So understanding when this actually extends would be a very nice open question. I think it's worth pursuing, I think. Yeah, so it just does not generalize, unfortunately, when you have multiple continuous constraints. All right. Okay, so that is like 1 hour from when we started. Should we take a break now, maybe?
Yeah, I think
it's a good time. Yeah, it's a good time. Oh, maybe I'll finish one thing. Just 2 minutes it'll take, and then let's take this break. This is important core.
Yeah.
All right, so let's just finish this corollary. So what we've seen till now is the following. If I take a polytope and I remove the interior of a finite number of convex sets from this polytope, and I take the convex hull of that, that's again a polytope. And also what we've seen now is that if I look at a set of this form where I have a convex set intersected with this equality constraint, where the equality constraint is defined by a continuous function, then this convex hull can be split into these 2 convex hulls, convex hull of S less than equals to with Fx less than Fx greater. All right. And so to prove the theorem, we really need this corollary. It's a set that looks like this. It's a set where X is at P, where P is a polytope, and Fx equals to 0. But additionally, now what we'll have is that F is a real valued convex function, such that this set Fx less than equals to 0, obviously it's a convex set, but it's also second order cone representative. Okay, and the corollary is that if you have a set that looks like this, so it's basically a set that is on the boundary of a second order cone representable set intersected with a polytope, then the convex hull of this guy is also second order cone representative. And why is this true? Basically, see, because F is a convex function, real valued, that implies continuity of F. And because of continuity, by this Richard Taverman lemma, we know that the convex hull of this guy can be split into 2 parts, Fx less than equals to 0 and Fx greater than equals to 0. The less than equals to part is already a convex set. It's X in a polytope, fx less than or equals to 0, which is second order cone representable. So that's just the intersection of a second order cone representable set with a polytope, which is again second order cone representable. On the opposite side, this greater than or equals to side, you have x in a polytope, fx greater than or equals to 0. But that's just saying it's x in P when I take away the interior of the set fx less than or equals to 0. Okay. But this is a convex set. This is a convex set. And P minus a convex set, its convex hull is a polytope. So this guy was SOC representable. This guy is a polytope. The intersection of these two guys is SOC representable. All right, so that is a good point. Let's take a 5 minutes break.
Yeah.
There is a question,
yes.
Santanu.
Yeah, I'll take questions. Yeah.
Sorry. Yeah, or maybe Gonzalo, you can unmute yourself and ask the question.
Sure. Hey.
Hey,
everyone.
hi, Gonzalo.
How are you? Thank you for the talk.
Oh, thank you. Yeah, for attending. Yeah, I like that haircut.
Yeah. Yeah. Quarantine happened. So I have a question. So you mentioned that this doesn't work when you have multiple equality constraints, but couldn't you just like square them and add them up and just get a single equality constraint that would emulate all of them at the same time? Why wouldn't that?
That's the first thing to try, right? But the problem is when you square things, the greater than equals to side is trivial.
Yes.
So that doesn't say anything about, it doesn't yield anything interesting.
I see.
Yeah.
Okay, but how about the other side? The other side would still.
The other side is just saying the sum of two sets. Yeah, but it doesn't yield. It's exactly the intersection, right? So saying some square term is less than or equals to 0 is.
Okay.
No. So it would be very nice if that trick actually yielded something. Yeah, it doesn't.
I see what you mean.
It's a natural thing to try. That was. I've also. Yeah, I tried that. Yeah.
Okay. Yeah, you're right. Okay, thank you.
It's very surprising that it goes through with one equation and not multiple. Yeah, so that's
Yeah.
Yeah.
All right. Thank you, Santanu.
Thanks.
Okay. Any more questions for now?
Yes, Sriram here. Hi, Santanu.
Yeah, Sriram, please.
Hey, hi, Sriram.
Yeah. So I was asking about the extreme points and boundedness question.
Okay.
So even if we do not have boundedness, can't we say something like this, that every extreme point of the convex hull of S less than or equal to, that will always be contained in S, and then potentially due to unboundedness, you might have an unbounded ray, which could be the single point that you could choose from S less than or equal to, something like that, or single direction.
So actually, to be honest, this result holds. Actually, this result. So here we are not using. I'll go step back. So these are the two ingredients we talked about, right? So this has got nothing to do with boundedness. Now this actually the proof does use boundedness, but in fact this holds true for general polyhedron as well. It's a paper that we are about to finish and post soon. So it requires a little bit more technicality. The problem is, if you remember the way we prove this theorem right now, we only counted the extreme points, right? And we just said it's finite.
Right.
But now when this is a polyhedron, this set is a non-convex set. And then you really have to worry about, it's very easy to basically use the same machinery to argue that the number of extreme points is finite. But you still have to argue that the convex hull of the resulting set has a polyhedral recession cone, and that needs a little bit more machinery.
Okay, but the question I'm asking is actually in slide 92, the claim 1 that you have there. Yeah.
Yes.
So the claim 1, I was just suggesting, if this comes through a more easier proof, or if there is a flaw with that proof idea which I'm suggesting.
Oh, what is the proof? No, I'm sure that you have a proof idea. These guys already had multiple proofs on this. I just picked the one which I understood best. But go ahead.
What I'm saying is, since x0 belongs to convex hull of S less than or equal to, now considering the set of extreme points of this object, convex hull of S less than or equal to.
Okay.
I'm saying this, the set of extreme points is contained in S, because S is like the boundary of S less than or equal to. So if you have boundedness of S less than or equal to, you don't even need this clause that at most 1 point. But if you don't have boundedness, then yes, you know, apart from the extreme points, you need.
I see what you're saying. Yeah, that's true. That might be true. Yeah, there might be a way to work that. Yeah, you're right.
Mm-hmm. And that one other point can be chosen, you know, along the extremal direct ray in S less than or equal to.
Okay. Okay. Maybe that's, yeah, that seems like that might work. Yeah. Okay. Yeah. That might work. You have to be a little careful in the unbounded case, but definitely the bounded case, I agree with you. Yeah.
Thank you.
Yeah.
We also had a quick question from Michaela, which Ahmad seems to have already responded to. So you happy with that, Michaela, or would you like to?
Hello, Santanu.
Hey, hi, Michaela. How are you doing?
I am listening, holding my breath. Is it clear that if P is a polyhedron and you remove the interior of convex sets, you get a closed set?
Oh, no. Okay. So, yeah, I cheat. My bad. You were right. No, it is not a closed set.
So, closed.
The closed, of polyhedron minus a finite number of convex sets is a polyhedron. Yes, you're right. I should, in the general polyhedron case, I should take closure. You're right.
Yeah.
Okay, thanks. So let's let Santanu out for a short break, and then let's continue in a couple of minutes.
Okay, all right. Yeah.
Or, I mean, we can also continue right away, but
yeah, just give me. I'll
just a little rest.
All right, thanks. All right, so let's get started. All right. Okay, so we have about we have enough time. So let's go through this very quickly. Again, I assume most people here know this. I'm just going through this because if you haven't seen second order cones, this might be a little. Yeah, this might seem a little strange to you, but it's not so strange. We already know in the case of polyhedra, for example, that the closure of convex hull of union of polyhedra is again a polyhedra, and it turns out for conic sets there's the same thing. But since we'll be dealing with bounded sets, in fact, you don't even need to take closure. So let me just very quickly do this. So if you take two sets, which are conic sets. So again, remember a conic set is nothing but you take X, you take an affine image of that, and that must live in your favorite cone, which is closed, pointed, convex, and maybe you have even two different cones here. And then it turns out if these are bounded sets, the convex hull of P1 union P2 is precisely the projection in the X space, where this is the standard trick in integer programming, we reference Egon Balázs for this, but this kind of works in this conic setting also, where you basically introduce new variables for each of these sets. So x1, x2, you homogenize the right-hand side. So you have this lambda 1 minus lambda, and then you just say that this x here is the sum of x1 and x2, and this lambdas must add up to 1. Oh, I forgot to write that here. Oh, that's right. Oh, yeah. So I've used the same lambda, so they add up to 1, obviously. 1 minus lambda plus lambda, and lambda is 0. And why is this useful? Well, this is useful because if K1 and K2 were just product of second order cones, then actually this set here, this is just polyhedral, and each of these constraints is again second order cone representable. And so what it tells you is that if S1 and S2 are two bounded second order cone representable sets, then the convex hull of S1 union S2 is also second order cone representable. Okay, and yeah, we have about 50 minutes, and I feel like if I only wanted to finish at the end of the theorem that I stated, then I would go through the proof. But I feel like this most people know. And anyways, I put the proof explicitly here. So let me skip the next few slides, which is basically proving this. But this proof is, if you have written this proof ever for a polyhedron, the proof is exactly the same. It is exactly the same. Okay, so it's just exactly precisely the same. And you know, the special case, you know, when lambda is between 0 and 1, you just rescale things easily. When lambda is at the boundary, you just have to prove the other guy is 0 because of boundedness. Exactly the same proof. All right, so let me skip this. All right, so these are the three main ingredients. In fact, the corollary of the first two ingredients and the fact that convex hull of union of SOC representable sets is again SOC representable. Based on these three results, we will prove the theorem. All right, so this is, so as I said, what we want to prove is that we have a set which is the intersection of a polytope with one quadratic equation, arbitrary quadratic equation, arbitrary polytope, and we want to prove that the convex hull of the set is second order cone representable. All right. All right, so basically we saw these three ingredients. There's one more observation that we have to make, and that's given in the next slide to prove this theorem. But before I make that observation, let me just give you the high-level building block. Again, we use the same machinery. All right, it's a one-trick pony. It's the same trick. You want to understand the convex hull, understand the extreme points. So if a set is compact, then the convex hull is the convex hull of extreme points of the set. So now, notice the following. As a corollary of this, suppose I take a set S, I look at its extreme points, and I take the extreme points and I put them into M buckets. Now, I might put stuff that is from S that is more than the extreme points, but I just take basically M buckets and I put some points in each of these M buckets. I make sure to include all the extreme points, but I might include some other points from S. Then it's clear that the convex hull of S is clearly the convex hull of the union of convex hull of each of these sets. Because I mean, the first thing to see is that if I remove this convex hull, the statement is true. If I just stick in a convex hull in between, you know, I don't get anything more. And so the convex hull of this set S is nothing but the convex hull, the union of convex hull of each of the points in these buckets. But then if this convex hull inside this union was second order cone representable, then from what we just saw, the convex hull of finite number of a union of finite number of second order cone representable sets is again a second order cone representable set. And so we would get that the convex hull of S. So basically the way we prove this result is by basically taking the extreme points of that set and putting them into somehow these buckets such that we show that the convex hull of points in each bucket is second order cone representable, and so we are done. So that's our task, to find these set of points which contain all the extreme points and that can be put into these buckets where each bucket's convex hull is second order representable. All right, so here is the observation that we need to in order to put these into these buckets. So it turns out here's a property, a sort of a structure lemma, if you may, about quadratic functions. So if you take a set defined by a single quadratic equation, then exactly one of the following three things occur. Either it's the boundary of one second order cone representable set. So in fact, it's essentially the boundary of an ellipsoid type set, or it's the union of boundary of two disjoint second order representable sets. So this sort of, the way to think about it is these two sheet hyperboloids, where each of these parts of the hyperboloids is second order cone representable. It's a convex set. Together it's not a convex set, but each part is a convex set. In fact, not just a convex set, it's second order cone representable. And it's the union of, so, and it's the equation, so it's the boundary of these two guys. Or a very surprising thing happens. So if it's not these two settings, you take any point in the surface of this object, in other words, any point that satisfies this quadratic equation, then you can draw a straight line through that point that is entirely contained in the surface. In other words, if you're not in case 1 and case 2, so this is clearly not true here. If you take a point on the boundary of the ellipsoid, you cannot draw a line through that point such that that line lives on the boundary of the ellipsoid. That is clearly also, you can check, is not true here. But it turns out if these two things don't happen, then if you take any point that satisfies this quadratic equation, there is a line that passes through this point. That line also satisfies, every point on that line also satisfies this quadratic equation. And actually these objects have a name. These are called as ruled surfaces. And this is my favorite picture of the talk. You see that this is essentially hyperboloid, a handmade hyperboloid by straight lines. Basically, you take these bamboo shoots and you stick them in the right way. You basically get this this sort of one-sheet hyperboloid. And basically what it's saying is if you take any point on the surface of this hyperboloid, there is this bamboo stick. The stick is telling you which is the line that lives on the surface. Okay? And so it turns out quadratic functions, you can always put them into any of these three buckets. And that will be sort of key in proving the theorem. And in fact, we are now ready to prove the theorem. We have to still prove this lemma, which I'll get to later, but let's prove the theorem. All right, so here's what happens. I give you your polytope and I give you your favorite quadratic equation. Now, if you're lucky, you are in case 1 or case 2. Remember, case 1 is when the quadratic equation is the boundary of a second order cone representable set. Or case 2, it's the boundary of the union of two second order convex sets, representable sets. And in that case, if you remember, we did this second order cone boundary corollary. So let's consider case 1. You are now the boundary of a second order cone representable set intersected with a polytope. And we know that the convex hull of such an object is second order cone through this corollary. Or you're the union of, in case 2, you're the union of two second order cone representable sets boundary. Take each of these pieces separately. It's the boundary of one second order cone representable set intersected with a polytope. The convex hull of that is second order cone representable. And then you have to take the convex hull of the union of two second order cone representable sets, which is again second order cone representable set, and so you're fine. All right. So if your quadratic equation happens to be in case 1 or case 2, then basically from the machinery that we've seen before, this second order cone boundary corollary, union of associated representable sets, we are done. So what happens? If you're not in case 1 and case 2, we know we are going to be in case 3. But let's think about what happens in case 3. So if you take any point in the relative interior of your polytope, but on the boundary of this, so it's a feasible point, which is on this quadratic, satisfies the quadratic equation, and is in the relative interior of the polytope. Well, what do I know? I know it's a ruled surface. So I know that through this point, I can draw a line which remains on this quadratic surface, right? So what does that tell you? Because I was in the relative interior of the polytope, that tells me that this point cannot be an extreme point of the set.
Sorry, Santanu.
So let me repeat that again, maybe. Sorry, I fumbled over too many words.
So sorry, there was just a quick question.
Okay.
Whether back to the previous case, can you decide whether you're in case 1 or in case 2?
As it turns out, you can, because this structure lemma actually is related to eigenvalues of the quadratic, and so you can.
Thanks.
Exactly. And so now what is happening is you take a point which satisfies a quadratic equation, but is in the relative interior of your polytope. Well, what I know is that I can draw a line now that lives on the surface of the quadratic. And since I was in the relative interior of the polytope, that means this point here that I have is not an extreme point. In other words, if I'm in case 3, any point in the relative interior of the polytope cannot be an extreme point of my set. What does that mean? All my extreme points must live on the facets of the polytope. All right. So what I do is I recurse. I just go into each facet of the polytope. Now what I have is this polytope in one dimension lower, intersected with the quadratic. So I can fix one variable, like, there's two equations. I can fix some variable. I get a new quadratic in a new polytope. And basically what I do is I just check if I'm in case 1 or case 2 or not. If I'm in case 1 and case 2, I convexify that set. So I've convexified all the extreme points that I would obtain on that facet, because I've convexified probably more points. But if I'm not on case 1 or case 2, then I can further recurse and go to the facets for the facet, which are lower dimensional faces, and basically sort of recursively go through the face lattice. In other words, what happens is the following. What is this proof saying? Is that if you want to convexify this quadratic equation intersected with the polytope, basically what you have to do is look at all the maximal faces of your polytope, which the quadratic is in case 1 and case 2. And for each of these case 1 and case 2, you can actually, by this SOC boundary corollary, you can get the convex hull, and this convex hull is SOC representable. And then what you do is you take each of these SOC representable sets that come from each of these maximal faces, take their union, and take the convex hull again. This way you would cover all the extreme points of your set. But we know that the convex hull of union of SOC representable sets is SOC representable, and therefore we can do that. Okay? So basically the key point is if you are in case 1 and case 2, you're done. And if you're case 3, well, there is no point in the relative interior of that face that is extreme. So you can just forget about all the points in the relative interior of the face, and you can recurse to lower dimensions. That's the argument. Any questions? All right, great, fantastic. Oh, Gonzalo has a question.
Yeah, can you hear me, Santanu?
Yes.
Yeah. So could you use this same idea that you're building here for, for building the whole convex hull, but instead, let's say you just want a facet. You just want one facet of your set. Could you just use the same recursion and then just merge them back together and just get one facet, for example?
What do you mean facet? You mean a valid inequality for the convex hull?
Yeah, exactly. Well, yeah, they might not have facet, but yeah, a tight valid inequality for the set. Yeah.
And your question is? Sorry,
So if you would use the same thing, you could use the same procedure that you use for building the whole convex hull, but just to build one of these inequalities.
You could, for example, of course, somehow check the validity by just looking at these faces. Exactly.
But you would check validity. Can you construct it?
Yeah. So I haven't really thought about it that way. It is constructive in the sense that I'm saying that I can keep like going, look at the polytope, I look at the quadratic in the n dimension, see if it's in case 1, case 2, or case 3. If it's in case 3, I just go down to the faces. And then in each face, I readjust the quadratic to that lower dimensional space, check again, and sort of recurse. But I don't know to build it other way around. Like I haven't thought about it.
Yeah, I mean, I was thinking more, if you have, let's say, a vertex or something, a point that you want to separate from this convex hull, and you don't want to construct the convex hull completely, you just want to separate this one point and do it faster.
Yeah. So it would be nice. Yeah. So no, if you have some ideas about that, I'm all ears. Yeah. I haven't thought enough about it, but yeah, if you have some ideas, that would be very interesting because. So what I'm not presenting here is we actually, in one of the papers, there's a special case for this. We actually implemented it. We write the convex hull, and it actually helps in the computations in dual bounds significantly. But in that particular example, what happens is that each of this quadratic, so there's a bunch of quadratics, and there's some polytope, and each of these quadratics is very sparse. So there's just very few. There's like 5 or 10 variables in each equation. So I can do this expensive procedure and actually find the convex hull of each row and throw it in. And
I see. I see.
But I would really love to be able to take this and convert this into a more efficient separating algorithm. Even if it's exponential in theory, but if it's more practically useful, then that would be very nice. Yes.
Yeah. Okay. We can chat later.
Let's chat later. Yeah.
Santanu, just another question from the chat. Does this apply to the inequality case, namely if x ux plus alpha x is at most g instead?
Yes, it does. It does, and you can see it in two different ways. One is basically a similar proof would go through, but if you can also directly get the inequality case as a corollary, because what you would do is, if you have an inequality, just add a slack variable, make it equality. Now, because everything is bounded, the slack will also be bounded, and so you would basically go from an inequality setting to equality setting, where again, all the variables are bounded. In a polytope, and the slack will be in an interval. And so now you can apply this theorem, get the convex hull, which is second order cone representable. And therefore, of course, the projection without the slack is also by definition second order cone representable. And so yes, this theorem is true even if you have inequalities. Are there any questions?
Yeah, thanks. I guess any other questions? So, yeah.
All right, let's go ahead. So then all I have to show to you is basically this structure lemma that every quadratic, essentially it's about quadratics. Every quadratic, when you look at the equation corresponding to it, falls in these three categories. And this is a lot of calculations. I'll not show most of the calculation. Basically, what you do is the following. You basically just say that, look, I take my favorite quadratic, and what I can do is I can apply an affine mapping, bijective. If I apply a affine bijective mapping, then all of those cases will remain if and only if. And so what I do is I take my favorite quadratic that I'm analyzing and apply an affine mapping to it and make it look like this, where I've gotten rid of Q, I've gotten rid of this, all of this stuff, and what I have is just positive square terms, negative square terms, linear terms is equals to right-hand side, which is non-negative. And basically, if I show that for this case, only case 1, case 2, case 3 can happen, then because I applied a bijective linear affine map, the same holds for the original T, and I'm done. So really, all I have to do is prove that structure lemma for something that looks like this. And you see that these are the eigenvalues. This is the signature. This is NQ plus is the number of positive eigenvalues Q had. NQ minus is the number of negative eigenvalues you had. And essentially NL, that is the remaining guys, is a set of 0 eigenvalues. And it turns out literally you have all of these 5 cases which cover all possibilities of the number of NQ plus, NQ minus, NL, where you could check explicitly that you are in case 1 or case 2 or case 3. And I wouldn't go through all of them because most of the proofs are easy. But since it seems we have a little bit of time, let me just show the last case. I mean, I have the slides for the last case. I think we have time to see it, that's the only case that is a little interesting. So that's the case when you don't have any linear terms. So basically, you can think of this Q to be full rank. And the number of positive eigenvalues is at least 2, and the number of negative eigenvalues is at least 1. And this right-hand side D is non-negative. And then we want to show that this quadratic equation, if you take any point on it, there's a line through it. And it's mostly a lot of calculations, but let me try and show this last case. So basically, here's what you do. You have the set Wi square, xi square, at least 2 of them, at least 1 of these negative terms, and this is without loss of generality non-negative. Right-hand side is non-negative. So let me just take one point which satisfies those conditions. And what do I want to do? I want to construct some vector uv, which is not 0, such that this point plus lambda times uv, essentially this is the line that passes through this guy, also satisfies the quadratic equation. That's what I have to show. All right, so the case when this guy is 0, actually it's a trivial case, so you can check separately. So let's assume this guy is not 0. This original point that you're looking at is not the 0 point. All right, so in this case, because this is not the 0 point, if W0 component was 0, remember the equation is these guys minus these guys is something that is non-negative. So if this component was 0, the only way that can happen is if the x's was all basically 0 and d was 0. But then you would have w is 0 and x is 0, and you would go to the other case. So therefore, you can assume that w's are not 0. And then in that case, observe that, okay, so this square of the w guys is non-negative plus these guys. So I can throw away this d, I can throw away all these terms. I know there's at least one guy here, so that's x1 squared. So if I rewrite that, I get this expression, okay? The absolute value of x1 divided by 2 norm of these guys is less than or equals to 1. This will be needed. All right. Now let's just quickly see the algebra. So now how do I prove something like this? I take these points here, and I just hope to find some u's and v's so that for all lambda I can satisfy this equation. What do? You just expand stuff. Okay, so that's what I'm doing. I'm just expanding stuff and writing things in terms of this lambda parameter. This guy is nothing but my original point. And so I just know I can cancel that. And this term is inside lambda squared. This term is inside lambda. This is 0. So the only way this will hold for all lambda is each of these terms is 0. So I need each of these terms to 0. I do some guesswork. And it turns out basically what I have to show is that I need some UIs that satisfy this, which is basically the boundary of a ball. And it must live in this hyperplane. But this hyperplane has this nice property that because the data somehow turns out just appropriate, that this hyperplane's distance from the origin is less than or equals to 1. But this is a ball in dimension 2 or more with radius 1. And so they must intersect. And so therefore, there must be some real values of u which satisfy this. And then you plug back everything and everything goes. So this is the only case where the proof is a little bit interesting. All the other cases, the proof is literally a lie. So it really goes through very easy. All right, so that's all I have to say about this theorem. Just a quick commentary about this result. So what we just saw is one quadratic equality or inequality constraint intersected with the polytope is second order cone representable. So I'm using an old notation here. Actually, it turns out when you have two quadratic inequalities under some technical cases, it has been proven by multiple people in different cases and different settings. So now I don't allow other inequalities, right? Just two quadratic inequalities. Under some technical cases, it turns out the convex cell is again second order cone representable. Okay, so one quadratic equality or inequality with polytopes or go second order cone representable. What is already known, there's a very nice paper by Hamza Fauzi, which uses this extended formulation machinery to prove that what he really proves is that if you take the SDP cone, the 3x3 matrix SDP cone, this cone does not have a finite side second order cone lift. In other words, the cone of matrices, 3x3 SDP matrices is not second order cone representable. But you can translate this into language of quadratics and say that there already is a 10 variable system with 5 quadratic inequalities, 4 quadratic inequalities, and 3 linear inequalities, which is not SOC representable. So, but there's a gap. So, for example, what if I take 3 quadratic inequalities, or 2 quadratic inequalities with side constraints? Is the convex hull second order representable or not? And so it would be nice to actually resolve this gap. I think that, in fact, it's really these guys that are second order representable. Anything more than that is not. But it should be verified by examples or proof techniques that we don't have yet. I also, this is a very highly incomplete literature review. I don't know if that's a useful thing ever to do, but still I'm doing that at the risk of, so what sort of results are known? As I told you earlier, there are these nice results about these hierarchies, the sum of square hierarchies and RLT hierarchies. But if you want to explicitly understand, these simple sets, can we explicitly give its convex hull? A large part of this literature comes from basically starting to understand what is called a generalized trust region problem, which is basically optimizing a quadratic over a quadratic constraint. This is called the generalized trust region problem. And there's a bunch of paper here, not all necessarily convex hull, but they basically look at this problem, they look at two quadratics, they start looking at multiple quadratics, they start looking at some side constraints, and they try and understand what the convex hull looks like. And there's a whole sequence of papers like this. These are some of them. There's a typo here, my Turkish I and C, my apologies. These two papers, there's other set of papers that just explicitly try and convexify one single non-convex constraint, like I had, together with some other structured constraints. So maybe the second one is a convex quadratic constraint, or the second one is a convex SOC constraint and things like that. So in some sense, the result I just presented is in this. But here, most of these results need SDPs or more to give the convex hull. I've highlighted these two papers because these are nice review papers, and they contain a lot of other references in them. And there's a bunch of nice results here. SDPs are quite good for solving QCQPs, and there's very interesting paper recently by Sam Burer and Yinyu Ye, which actually talk about random QCQPs, and they say something about somehow diagonal random QCQPs whose convex hulls can be obtained using SDPs. As I said, again, I'm not really talking so much about SDPs, and this is a paper that is accepted in IPCO this year, so I'm looking forward to that, which is somehow generalizes some of these results. And also, if you want to go approximations, this is just 3 papers. There's a whole world out there. In particular, I should have mentioned Gubens-Williamson here, because essentially that is also giving you a SDP guarantee about a QCQP set using SDPs. And then there's this Nesterov and Yinyu. This paper also has a lot of other references. And Bental Nemirovsky, the book they have, also actually talks about a number of references. But most of these results are SDP or SDP++, let's say, to describe convex hulls. All right, so I have about 22 minutes left, which is perfect, because now I can go back and actually finish all my slides. And so I'm happy that I actually have these extra slides. I want to go back to functions. So up until now, what we looked at was sets. So there's actually, as it turns out, even though this looks like a lot, most of this is SDP world. And also, there is far fewer results in the set world, convexifying sets and understanding what the convex hull of sets look like. A lot of the original global optimization literature actually still works with functions, which is also a very useful perspective. And so let's go back to this this function convexification that I mentioned a little bit at the start of yesterday. So these convex envelopes and concave envelopes of functions. So let's start with the sort of questions that people have looked at. So look at this function here. Now this function is again edge concave because each term is edge concave, and it doesn't matter if you're plus or minus sign. But here, as it turns out, I actually have a +5, +3, +7. But I know that this function here is edge concave for this set, and so I know that the convex hull of this function can be obtained by the extreme points of this set. But you see that now I have to look at 2 to the 4 extreme points. And as you see, this is a placeholder for more general things. If I have a general bilinear function using n variables, then I have to basically look at 2 to the n extreme points. So the way to convexify this in the correct way prescribed earlier is that you look at every extreme point of the box. And you want to find the convex envelope value at a certain x, right? You try to write that x as extreme points of these 2 to the 4 points. And for each of the 2 to the 4 points, you evaluate the function value. That's how you would do it, right? But now we know these McCormicks are there, and we know this term-wide convexification. So what I can do is something cheaper, right? I can write a convex hull that looks like that, which basically just looks at the convex envelope of x1, x2, convex envelope of x1, x4, and convex envelope of x3, x4. And I can basically get what is like a relaxation of the convex envelope of F using just these McCormick's. Now you see this is much more cheaper because here to get the exact convex envelope, I would need to look at essentially 2 to the n points. Here I just look at every pair. So this is just order n square work, right? So what I would get is obviously a function that is convex and lower bounding fx and concave and upper bounding f, but it would not be the best possible function because those are the envelopes that I can get from 2 to the n. But then of course, how good, the question is, if I just did this term by term n square convexification of this function, how good is this relaxation of the original actual convexification? That's the question. And so, this is a very nice result, and I sort of referred this result for the packing, but really this paper by these guys is this is the theorem they have, and the other results that are related, Kramer's result and then this related result, which basically says that if you have a function of this form, where each of the aij's are non-negative, then the concave envelope, not the convex envelope, okay, you have to be careful, only the concave envelope, which means that the function that is larger than fx and is concave, this concave envelope can be obtained by just looking at the concave envelope of each of these terms by McCormick and just adding it up. Okay, so let me repeat it again. In order to find the concave envelope of this exactly, what I would have to do is basically look at the 2 to the n extreme points of this box. But if the data is non-negative, then it turns out I can get this concave envelope. If the data is non-negative, I can get this concave envelope by just looking at each term. And I think we have enough time. We have about 15-20 minutes. I think we have enough time to see the proof. So let's prove this. Why is this true? It turns out it's thanks to total unique modularity. And this is an exercise we've all done. This is some or the other time. For example, it's there as an assignment in Mauser-Wolsey. It's in some sense a consequence of total unique modularity in the following sense. So I have this function f. I have this function g. I'm doing it for, again, this particular example because coefficients are non-negative. All right. Now, because I want to find the concave envelope, I only care about maximizing this function. And I also don't care about writing the complete McCormick. I only write, because I'm maximizing, I just have to stop these W1s, W2, W3 to not be too large. So I just have to say W1 is less than X1, W1 is less than X2, W2 is less than X1, W2 is less than X4, W3 is less than X3, W3 is less than X4, and some whatever, the bounds on W. And this basically solves the problem. All right. Okay, this gives me essentially the McCormick-based envelope. This is I want the exact envelope of F. All right, so now let's take a point x hat, okay, of F, and for that particular x hat, that's the right hand side of this LP, let W hat be the optimal solution of this LP. Okay. So because this function is concave, trivially, of course, we know this inequality holds. This is it's a concave function. It's definitely a worse approximation than the actual concave envelope. What I want to prove is the opposite inequality. But here's the key insight. The insight is that this matrix here, I know I fixed x to x hat, but ignore that. Just think of this matrix in the space of W and X, then this matrix is TU. And because this matrix is TU, I can take this x hat, W hat, which is the optimal solution of this LP, which lives in this polytope, and write it as convex combination of points that are integral. Because I can always write this point as convex combination of extreme points of this polytope, and this polytope, because this constraint matrix in W and X space is TU, I can always write this as convex combination of integral guys. but that basically completes my proof, because the value of this McCormick, this guy, by linearity can be written in this form. But basically, what am I doing here? I am actually computing the objective function value at extreme points and taking their convex combination, and that's one particular convex combination for one particular choice of possible way to write this guy as integer points, and so I could do better, and so I get this inequality on the other side, and so I get the opposite. So again, there is a result in Kramer's paper, which is stated in a slightly different way, but basically it says that it holds for even not just bilinear, but even multilinear terms. It basically says that as long as these numbers are non-negative, and this, whatever the resulting relaxation is, like bilinear, you can write some relaxation for multilinear terms, as long as that object is integral, it goes through. And it turns out there are connections to these balanced matrices there, because for general multilinear, it's not to U, but you still get integrality through balanced matrices, and things go through. And so now you see that when you're analyzing these functions, there's much more connections to this IP in a very natural way. And so you can start now asking more generally. Now I don't want to, okay, so what happens if the terms are not non-negative, right? And then this is a statement only over the concave envelope. What about the convex envelope, which goes below the function? How good is that when these are non-negative? So you can ask all of these questions, and there's a very natural way to pose these questions, which was posed in this paper by Jeff Linderoth and Jim Lutke and their student. And I have 12 minutes, so I should be able to cover some of it. So here's what they said. So you take your favorite bilinear function that looks like this. Now the AIs could be positive or negative over this box, and you take a particular x hat. Now at this x hat, what happens is that you take the concave envelope, you take the convex envelope, and you can take the difference of these two. Remember, for example, if you are at any boundary, the convex and concave envelope will be equal, and this value will be 0. But in between somewhere, it is not true that the concave envelope and convex envelope will match up, because the concave envelope goes above f, convex envelope goes below f. So remember again, concave envelope is the sort of the smallest concave function above your function. Convex envelope is the smallest convex function below your function. And so at any given point, somewhere in the interior, there'll be a difference in value of this concave and convex. But this is the ideal gap, because that has to be there. But now what you can do is you can take term by term, you can write the McCormick inequalities, and you can get a relaxation. You can get another concave function that is not the best concave function above. You can get a convex function that's not the best convex function below, and you can ask the gap between these two terms. I call this the efficient, and this is the ideal, because this would take 2 to the n computation. This efficient I can compute in n squared time, because this is just the McCormick evaluations. So clearly this efficient is larger than this ideal. But how large is it from ideal gives you an idea of how bad is the McCormick. Is the setup clear? Any questions? The setup clear, right? So how bad is this? How much larger is this compared to this? Gives me a sense of how bad is the concave and the convex functions that I get from McCormick compared to the ideal concave and convex functions above and below this function f, which is given in this form. And the answer is very combinatorial, and I think a lot of people in this audience might appreciate it. So you think of the graph, where you think of the vertices of the graph being the variable, and remember it's this sort of bilinear function. There are no degree 2 terms, so you're only looking at xi, xj's. So whenever you have an xi and xj, you put an edge in that graph. And what you do is this coefficient of xi, xj that is in your function, you put that as the weight on that edge. Okay, so there's a very natural sort of graph with weights of the edges that you can construct from this function. So again, every variable is a node, and whenever you have a term xi, xj with with non-zero coefficient. You have that edge, and that non-zero coefficient in the function is the weight. Okay. And so this is a theorem that some parts of it are there in this paper. This is and some parts are it's stated in this paper. This is as stated in a paper that I have it together with Natasha, Thomas, Marco, and Fabian. So it says that these two guys are equal if and only if this graph is bipartite, and each cycle in this bipartite graph has an even number of positive AIs and even number of negative AIs. Okay, so in a sense, basically, instead of just having xi xj's, if you actually had xi yj's, you had a partition of the variables, so that x's never multiplied x's and y's never multiplied y's. So there was a bipartition, and also whenever you had a cycle, so x1 multiplies y1, y1 multiplies x2, x2 multiplies y2, and then y2 again multiplies x1, then at least two of those guys is positive and two of those guys are negative, for example, in that case. Then it turns out the McCormick is exactly equals to diffusion. Okay. As I said, again, this is the statement is as is in this paper, but really, I might be missing references here because we've just started working in this area, but this is sort of parts of it is known in different papers, and I'm mentioning two others, but my apologies if I'm missing some papers. Let me at least state some more very nice results. In particular, this result that is one of my favorite results by Jim and their student Mahdi and Jeff Linderoth, which says that look at the case where AIs are non-negative. So remember, in that case, we proved that the concave envelope from the McCormick is the same as the actual concave envelope that you want, ideal concave envelope, but it's not true for the convex envelope. So the convex envelope from the McCormick's might be weaker, but it turns out that when AI, it's not so bad. In fact, it's related, you can relate it with the coloring number of this graph. So you take this graph, it may not be bipartite. If it's bipartite, notice if all the AIs are positive and it's bipartite, then these two are equal, right? But if it is not bipartite, then it's not so bad. In fact, what it says is this efficient, of course, is larger than ideal. We know that. This gap between the upper and lower bound of the efficient McCormick from the ideal, but it's upper bounded by this multiplicative term, which is 2 minus 1 over the chromatic number of the graph divided by 2.
Sorry, Santanu, there was a question whether the positive weight edges in this graph form a cut.
Sorry, if the positive weights?
So if you look at the positive weight edges in the graph, whether they form a cut, Ahmad was asking this.
Yes. That's true, yes. I think the way to see it is that you form an equivalence class between points where you have only positive weights, and look at equivalence class of vertices that have only, where you can construct a path with only negative weights. And then you can argue that this is. And just to see why this actually implies this theorem, in a sense, is that when it is bipartite, this is 2, so 2 over 2 is 1. So this is 1, and so the ideal is equals to efficient. So if A is non-negative and the graph is bipartite, ideal is equals to efficient. So it basically implies this theorem for the non-negative case. Okay? And what happens in the negative case? Unfortunately, the answer is not super nice. Basically, it turns out you can have a multiplicative error of the order of square root n. And in fact, this is tied up to multiplicative ratios. All right, so I have 5 minutes, and I'm trying to think what's the best way to. So I actually have explicitly, even if I'm not able to complete it, if you are interested, the next few slides gives explicitly the proof of this theorem. Let me see how much I can do. Okay, just maybe I'll there's a lot of algebra also that I like to skip. All right.
Sorry, Santanu, before you get into the proof, if there are any more questions at this point.
Yes, that might be a good. This might be a good time to take some questions, actually. Yeah. Yes, Ahmed.
Yeah, sorry, I can't raise my virtual hand as a co-host. So, could you go? Yeah, so in that slide, do you also have a condition on where the positive weight edges could perhaps be? Oh.
No. This is.
Oh, sorry. I think I misunderstood that result. Sorry.
Yeah. This one is only non-negative. Yeah. And this is in general without non-negativity. Yeah.
Thank you.
Are there any other questions?
All right, then I guess.
Okay. So I mean, it's a long, it's a non-trivial result with lots of things, but I'll try and highlight some of the interesting ideas, and there's a lot of other calculations and other stuff that go on. Okay, so obviously this part is trivial. So really, what we want to prove is that this term times the ideal is larger than the efficient. So that's what really we want to prove. So the first part of the proof really says, okay, so I have to optimize this over this continuous set, and that's going to be too difficult. But what we're going to say is that it turns out we will be able to reduce this to a finite set of points to look at. Okay, and what's the proof? This I think we should be able to finish. The proof is easy-ish. Okay, infinite to finite. Basically, what Jim and et al. Proof is that essentially it is enough to look at just points 0, 1, half, 1, and then that proving this is equivalent to proving this. Okay, so how to do that? This is a very ugly large term, so I'm just going to call that rho, and just remember that this is larger than 1 always. That's all I need you to remember. So I need to show that rho times this minus this. When I optimize over the 0, 1 continuous set, it's enough to optimize it over the 0, half, 1 set. Okay. So I have this thing here. Now remember, I'm looking at the case where all the AIJs are non-negative. Okay, so I expand this. What is this? Ideal is nothing but the concave minus the convex. Efficient is the concave from McCormick, the convex from McCormick. But since AIJs are non-negative, remember we've already shown because of this du-ness, these two guys are equal. So I can cancel out this, and remembering that rho is greater than 1, this problem reduces to minimizing rho minus 1 times the concave envelope minus rho times the convex envelope plus the McCormick lower bound. All right. But, okay, so maybe one quick statement. This McCormick, basically when we do McCormick, we're working on this polytope. Now, of course, I have to include these guys. I'm including these guys as well. So earlier, for the convex side, okay, this was a typo here, Yij. For the just non-negative concave side, I just needed these two, but now I'm looking at convex and concave. I have to include all the inequalities. This is my McCormick. So I can rewrite this optimization problem. I just replace this McCormick evaluation as just the evaluation over this polytope. So I can write this as just x times x comma y, where I still have this concave ideal minus rho minus 1 minus rho times convex ideal, plus I just add the AIJs times the YIJs that come from this, where over x hat and y hat. But what is this problem? This problem is an optimization problem over this polytope. This is just a linear term. But this here, this is non-negative. This is a concave function. This is a concave function. This is a convex function with a minus rho. So this together is a concave function. So this whole thing here, and this is linear, I'm trying to optimize a concave function, minimize a concave function over a polytope. And so what's going to happen? I can argue that I can always assume that the optimal solution is an extreme point of the polytope. And what are the extreme points of this polytope? Well, it's well known back from Padberg in '89 that this is a 0, 1 half polytope. And so therefore you can reduce this problem to basically proving this over just the 0, 1 half one. Okay. All right, so actually I've run out of time. I will just say that essentially what happens is, basically the way to, what happens, the reason you get this chromatic number really is, okay, so what happens is when you compare these two guys, the concave part is the same, as we said, because the AIs are non-negative. It's the convex part that's different. So what you do is for the McCormick, you can explicitly compute it because it's just an LP. It's for the ideal guy that you have to approximate it. And the way you approximate it is you basically take some x hat, and which is this 0, 1/2 pi, because that's all you have to look at. And for this x hat, you want to write this as a convex combination of 2 points of this 2 to the n polytope, and take the function value there. It turns out the right thing to do, the right 2 points to take is basically take all the components of x that was fractional, that is half. And on those nodes, you need to basically look at something like a max cut. And take those nodes and separate them in some ways and construct these points. So, and then what you do is you connect the max cut to the colorichromatic number, and everything sort of falls out. So, okay, that was a terrible way. I'm not doing justice to this beautiful theorem by these guys. I really like this result. And I will just say that to prove the more general result, or not the more general result, the result for the more general case, okay, so there's a lot of stuff going on here. And this might be of interest to people. To prove this more general result, we actually have to prove something about cuts again on a graph. And essentially what you have to prove is that if you have a graph with some weights, not necessarily positive, then it turns out there's always a cut where the following holds, that if you sum the weights on the cut and take the absolute value, this is at least 1 over square root n times the sum of absolute values of all the edges, all the weights in your graph. And so this is needed as a key ingredient in this more general stuff. But okay, so maybe I've already gone 2 minutes over, so I'll stop and thank you very much, and I'll take questions.
Thank you very much, Santanu. So I'd like to ask everyone to unmute yourself a bit and give Santanu a round of applause.
Thank you.
Thanks. So we have time for some quick questions, and after that discussion can continue on Slack.
I have a question. Again.
Yeah, go ahead, Ahmed.
So you meant if all the edge weights are positive, you can bound efficient of x as you can upper bound as a function of the chromatic number. That's a really nice result.
Mm-hmm.
Are there extensions of this to the case where not every edge is positive? Perhaps the positive edge weights, positive weight edges form a cut. Could that?
Yeah, no, there are no explicit structure results. So yeah, so the only other thing that we have is this, and I have to think a little bit about. It's been a while. But no, I think there is scope for much more interesting results that say that, oh, under this pattern, you can get still a constant bound independent of the data. That would be really, or independent of the dimension. That would be very nice.
Mm-hmm.
That would be very nice.
Dependent, independent.
Independent.
All right. I see.
Yeah.
If nobody else has any questions, I have one more question. Well, if that's okay.
Go ahead.
So can you just remind me what the state of the art was with the second order representable cone? So you said if there's up to 2 quadratic constraints,
if there are,
then it's
so what is
second order.
yeah. So what is, as far as I understand, and again, we take everything with a pinch of salt. What we saw is 1 quadratic equality, which can also be written as 2 inequalities with opposite sign. intersected with a polytope, or if
Yeah.
you just have two quadratic inequalities, no side constraints. Okay, and I believe there
I
might
see.
be a technical condition there. I might be skipping, but under these two cases, essentially, it turns out the convex hull is SOC representative. And there is this example from a reduction from this very nice paper by Hamza about extended formulations of the SDP cone, that okay, so if you have like 9 quadratics, 5 equalities, 4 inequalities, then it is not SOC representative.
And
So,
and you don't think for nobody's looked at 3 quadratic inequalities, you don't think?
I almost suspect it is not, but I don't know. I think it's more like you have to prove that it is not SOC representable. And I think that needs machinery. That needs kind of extended formulation machinery, right? You basically look at this lac matrix and then sort of machinery. That's how Hamza proves this result. But then it has to be even more, it has to be tighter in a sense to go through 3 quadratic inequalities.
Okay.
Yeah. In fact, my suspicion is just 2 quadratics with the right set of linear side constraints is probably not already SOC. But I don't know. I think it's very delicate and it breaks out. In a sense, at least we were very surprised when we got this arbitrary polytope, because when you look at these things, usually when you start writing the SOC hierarchy, the sum of squares hierarchy, it's just very difficult to guess that, oh no, actually it would not be this hierarchy. There is a SOC that already gives it to you in a sense.
I see.
And just to tell you what this quadratic inequality is, it turns out at the heart of the result is out of a lot of structure analysis. Basically, what you show is that there are you just take literally algebraic combinations of the 2 quadratic inequalities. Okay, like just λ1 times the first quadratic inequality plus λ2 times the second one, in such a way that the resulting inequality is convex. Like you cancel out the negative eigenvalues, and these are enough to give you the convex hull. That is what happens here.
Okay, thank you.
All right, thanks, and thanks all for attending the summer school. So, this is now finished, but it was just a warm up for IPCO starting tomorrow at 8:50 UK time or 3:50 AM
Atlanta time.
East Coast. So we'll forgive those participants from North America who may join in later. But anyways, thanks very much also to the speakers and
thank you, Santanu.
Thanks, Giacomo. Thanks, Ahmed. Thanks, Lassi.
Thank you, Santanu.
Thanks, guys. All right, so I guess we bye. See you tomorrow.
Okay, so see
you in the Slack, I guess. Yeah, if someone's still hanging out. Bye.
Bye.